Right. So we said in this video, we have a model that we have trained. And okay, trained in quotations, right? We have trained our model. Now we are getting to where we are generating text with the model. But before really getting into the crux of some of those parts and saving the model and all of that, we want to tweak the model a bit because we say this model is generating text based on probabilities, and it selects the token, the next token with the highest probability. But sometimes we do not want that. We actually want to control some randomness, and we're going to introduce two decoding strategies. So they are called decoding strategies. And these decoding strategies are we are going to introduce them in the in our generate text sample or simple function, where we'll see it being applied, and then we'll see how it generates something different. We're going to cover two of these strategies with the temperature scaling and top case sampling. So temperature scaling and top case sampling, they create a bit of randomness. So if we to just discuss the first one that we are going to discuss is just temperature scaling. That's what we are focusing on in this video, and in the next video we'll do top K. So temperature scaling pretty much is trying to get rid of that. The generated token is selected at each generated step corresponding to the largest probability, but we want to introduce a different way of doing that. We were using argmax. We're using argmax, and now with temperature, we're introducing a technique that adds a probabilistic selection process to the next token generation. So probabilistic selection uh, of the next token, because what we were using was that argmax, and we said this is called greedy decoding. It just selects at every step, at every iteration, it takes the one with the max probability all the time. So what you end up with the same starting context, you will always have the same result because the probability will not change. The model has already been trained. The probabilities are going to remain the same in the vocabulary. So now when we put the same starting context, it will always predict the same words. And we'll see that in code. So to generate text that has a bit of variety, we can replace this argmax here by something called by something called multinomial. And this multinomial function, it samples from a probability distribution, and the probability scores that the LLM generates from the vocabulary. So it samples from that samples from a probability distribution. Let's see it at work. Probability distribution. So if we look at a simple example, imagine that we have a vocabulary that is these words: closer, representing zero, token ID 0, every, word code every, or token code every, token ID 1, and effort, token ID 2, forward, token ID 3, inches, token ID 4, moves, token ID 5, pizza, token ID 6, and then last one, last two anyway. Toward, it's token ID 7, and then you, token ID 8. And then we'll have, of course, have our inverse dictionary, our inverse vocabulary. So now what we can do is we can use the next token to predict the next token, right? Use the model, predict the next token, start off with every effort moves you, whatever it's going to be. It gives us back logits. And these logits, they are converted to probabilities using softmax. Normal process. And we get our token IDs, and with our token IDs, we generate text via that inverse inverse vocabulary, which is just defined as V to K for K V in vocab dot items, right? So it just sort of like reverses the order. So now the key is the is the V, and then the value is the K in that case. Cool. So now that we have that, we know how it works. Token IDs are produced. We produce the text, well and fine. So now when we want to implement this probabilistic sampling, we can replace that argmax with that multinormal. And what then happens is, in the background, what is happening is, if we put something like every effort moves you, and then this is our start context, right? And we put it in our model, we put it in a well-trained model, it's most probable that it will predict the word forward. But with multinomial, it is not all the time that it's going to produce forward. With argmax, yes, but not with multinormal. It's not going to happen all the time. Forward is still the most likely, but if you run this experiment many other times, you might start seeing other words coming through. For example, in our dictionary, you might actually see it say every effort moves you toward instead of forward. It will bring the word toward, because toward it happens, might not be happening many times, but it does happen. So that is what temperature is doing. So let us see it in code so we can explain a bit about what I'm saying just now. So let's switch to Chrome now. Perfect. So this is our vocabulary, right? Just the one that we have just written. And this is our inverse vocabulary definition there. So suppose that we have this every effort moves you, and the LLM, it returns this as the next token logits. These are the next token logits. It has predicted them as the next tokens. We can get the probabilities by applying softmax. Then we have the next token ID using argmax. And when we print what the next token ID using our inverse vocabulary, to say, okay, what we have the next token ID, what is the actual word in our inverse vocabulary? We get the word forward. Perfect, because that is the one that is argmax. Makes sense, right? Because even if it makes sense, because when you put even the logits themselves, you can see that the maximum logit is 6.75. So it's in index number 0, 1, 2, 3. And in our particular dictionary here, it's 0, 1, 2, 3, which is forward. So with argmax, because it's greedy, it always return forward. But we want variety, right? That's where now we replace argmax with multinormal. Here the seed is just for it to be reproducible. So we now say multinormal instead of argmax. On our probabilities, number of samples that we're returning only one sample, because that's what we want from our multinormal. We don't want it to return 2, 3, or whatever. We just want it to return the next word, right? So one sample. Perfect. And then we print what the next word is. Now it is printed toward. It is printed toward. Most of the time it will print forward, but sometimes it will print toward. Let's see how that is distributed. So if we run this experiment a couple of times, so here we are going to just we are using these print sample tokens. So let's say we run this experiment a couple of times. Here we are just going to sample 1,000. So we're going to run it maybe 1,000 times. Let's see how it's going to be distributed. So 71 times it's going to predict as the next token is is closer. And then 2 times it will predict it as every, then 0 times effort. Of course, every effort moves you towards, moves you. So every effort moves you, it will predict closer. It moves you every 2 times, effort 0 times, forward 544 times. moves you inches, moves, moves you pizza 0 times, moves you toward, makes sense, 376 times. So there's a bit of thinking that is going on there. Those words, they do make sense. Moves only 4 times. So this is when we run it 1,000 times. If we're using argmax, you can change this if you want. Change this to for it to use argmax. You see that it will all 1,000 times it will return the same value. So now that we have that, we can then create this temperature, and we are going to now discuss something called temperature scaling. So let's quickly switch back here to just write something. So now that we understand what multinormal is doing, so sometimes it will return statements like every effort moves you toward, and sometimes every effort moves you closer, instead of our one that we had predicted with argmax saying every effort moves you forward. So it sometimes changes, right? And we can control the distribution and selection process even further by using temperature scaling. Temperature scaling. Instead of just doing that multinormal, we can add what is called temperature scaling, and that is the crux of this video. So temperature scaling is just a fancy way of saying divide the logits by the number by any number greater than 0. So here we're going to divide logits by a number greater than 0. That's pretty much it. That's how we were going to scale. That's the scaling part. So if we have so we have our logits, right? So when we have our logits here, we are going to divide them by a number. If we divide them by a number that is greater than 1, this results in more uniformly distributed token probabilities. Why? Because imagine we are dividing them by 5. You remember the logits that we had. Let me actually write what the logits that we had were. Let me actually write them so maybe it will make sense. You remember when we did the next token, we got that we put every effort moves you, and according to our dictionary, we got these as our logits. 0.89 minus 1.90, 6.75, and then 1.63 minus 1.62 minus 1.89, 6.28, and finally 1.79. These are the logits that we had. So these were the next token logits, and we chose this one here because that was the highest logit, or when we put softmax, gave us the highest probability. So what we're saying is now we want to divide this by a temperature. So we're going to divide this by a temperature value. Temperature value. If the temperature value that we are going to use, if temperature is greater than 1, so e.g., if our temperature is 5, we're going to do 4.51 divided by 5, 0. Divided by 5, this divided by 5. This 6.75 gets much closer to the 4.51, right? You can do the calculation right now. When you divide by numbers that are greater than 1, and then you put them into softmax, it results in more uniformly distributed token probabilities. They're now more uniformly distributed. Some of them are much closer to each other than they were before you used temperature. And that increases variability. Increases variability because now the model, it has many that are looking the same. So it can choose tokens, it can choose many different tokens. Instead of, if it's less, temperature is less than 1. If temperature is less than 1, if temperature is less than 1, for e.g. 0.5, this is the same as multiplying all of these by what? By 2. So when you multiply this by 2, it will be around 9. But when you multiply this by 2, it will be around 12 and all of that. So temperature that is less than 0, less than 1, it blows up some logits more than others. And their probabilities are actually increased more than others. So this reduces variability. Because now the model will say, I'm only going to take this one 90% of the time, because with probability, with my multinormal and probability, it just makes sense for me to take this one. They are not similar, they are not uniform, so this is the only logical choice, so it will take that one. So this becomes more deterministic. So yeah, increasing how it can be deterministic. This increases, if your temperature is greater than one, it increases variability. Of course, in normal setups, if you go to ChatGPT, it doesn't really say temperature greater than one. There's just a bit of scale to make it easier for people. They just did the temperature to be between 0 and 1, and then the hotter you put it towards one, it becomes hotter. But actually, what you'll be doing is increasing this variability. That's all you're doing. It could be written in a different way, but that 0.7 could actually be linking to a temperature of 20 or whatever it is. I do not know what they have in the background, but you get the idea. So we probably won't be 20, but I think you get the idea there. So this increases variability, and then you get more creative texts, more creative texts. Some of them will now start being gibberish because it doesn't make sense, but yeah, it becomes more creative. So that's what happens. A temperature, of course, a temperature of one, just divide these logits by one before passing them to softmax, so it doesn't change anything. That is the same as just applying argmax. So you have the original, so original probability scores. Let's just see in code what I've been saying here. Right. So here we are going to create this softmax with temperature. We're going to have our logits that come out of our model, and we are going to have a temperature. So the scaled logits are going to be the logits divided by that particular temperature we are going to put, and then we just return the softmax, so which are our probabilities. We are applying them on our scaled logits. Easy. So now we are going to test three. You can test as many as you want. Yeah, I'm just testing three: 1, 0, 1, and 5. So this being 1, we expect it to just return as if we're running argmax. This is a low temperature less than 1. We expect it to be more deterministic, probably closer to the results that as if we are not doing any scaling at all. And then this is 5. This is 5, where it's more creative. This is higher confidence and lower confidence. So cool. We have a scaled prober. So this is softmax with temperature for next tokens T for temperature in for T in temperature. So it's going to take this temperature, run this function, put it in the list, run the function again when it's 0.1, put it in the list, and then run the function again when it's 5 and put it in the list. So now we have a list of temperatures, right? Of softmax with temperatures. Let's plot them. So when we are plotting them here, you can see when the temperature is 1, forward, that's the blue line, forward will be predicted 60% of the time. And then closer here, around maybe like maybe like 5%. And then toward will be predicted around like 30 something percent. That's what we can see here. That's when the temperature is 1. And that's when, as if we are using argmax, we didn't change any, we didn't scale anything. Now, when we apply 0.1, we're making it more deterministic. We are removing variability, right? Because when it's 0.1, we are blowing up the probabilities for some tokens and reducing for others. So as you can see, forward is now being predicted almost all the time, like 99% or 98% of the time, because the temperature has been reduced to 0.1. So it's not creative at all. It's not creative at all. It is quite deterministic. But when we put the temperature up to 5, we said it divides the logits and then becomes more uniform. It spreads out the probability. So as you can see here, now there's some green lines coming up for closer, for even effort. So even when we say every effort moves you, even effort itself is now coming up because the temperature is high. Now we are uniformly distributing that probability. As you can see, forward is reduced its probability and all. You can see forward and toward are now actually competing. So what we can see is sometimes now when we have our print sample tokens with our scaled probabilities, if we are using the scaled probabilities for when we have 0.1, you see all of the predictions are pretty much going towards forward. and then some are going toward because when the temperature is zero point 0.1, we have reduced variability. It becomes deterministic. Chase is one. Chase is sort of one token. But then when we have a temperature of 5, which is scaled proba, it is in the second index, right, of our list here of this scaled proba list that we created here for the different temperatures. So we take those and then we print the tokens. You see how variable it is. We have 153 of closer, 68 of every, 223 of forward, 218 of towards. That's why these ones can compete. Depends on where the story will take us. So assuming that this an LLM input every effort moves you, we see that when we have when we have this type of probability now of a high with a high temperature scale, we'll see that pizza actually comes up. Pizza will start coming up. It will start coming up here. Yeah, it's just because of the instantiation, but it will come up like 40 times, 40%. Yeah, it's 40% of the time. Every effort moves you, Peter. It becomes very creative, but sometimes very gibberish. But I hope you understand now what temperature does. That is the impact of temperature. In summary, impact of temperature is after your model spits out these logits, the temperature scale will just scale the logits depending on the value that you put, which would then affect the probabilities, which will affect your output token in this particular fashion. In the next video, we're going to look at another way of introducing this randomness, which is called top K sampling. So stay tuned for that video.